morning.
Yes,
Yes,
sir,
sir, you
audible.
are audible. Good morning, sir.
I will try to share my screen. Just confirm me if it is visible to you. Is it
Yes,
visible?
sir, it's
Okay.
Yes, sir.
Okay. Then let us start today's. So this is the fifth lecture. Okay, for this six lecture course. This is the fifth one, and what this slide, whatever I am showing, is the material of the last class. Okay, that means last Sunday we have covered it, and if you recall, we in the first lecture was all about introduction of CFD, its applications, what are the requirement for understanding CFD. So that thing we have discussed in the very first class. In second class, we are discussing about the governing equations. Okay, so that means Navier-Stokes equation mainly, and it is a partial differential equations, a set of partial differential equations which are non-linear and coupled. Okay, and we need to, our ultimate objective of the CFD is to solve that set of Navier-Stokes equation along with continuity equation. Okay, and that equations we have seen, and then we understood what are the steps. Okay, so we have seen that you need to convert the differential equation to algebraic equations by using a suitable discretization scheme, and that discretization scheme may be finite volume method or finite difference method or finite element method, like that. And in last few classes we have discussed two category. One is finite difference method, another one is finite volume method. Approach is little bit different, but basically finally the solution will be similar, quite similar. You will finally get a set of algebraic equations, linear algebraic equations, which you need to solve. Okay, uh, so that was the step, and another part was that you need to discretize the geometric domain. Okay, so what are the steps of CFD? Let us recall once more. You have to first construct the geometric domain, number one. Number two, you need to discretize that domain into a number of points or elements, or a number of small volumes. Okay, so if it is finite difference, you just discretize the domain with a number of points. If it is finite element, then discretize the domain into a number of small element. And if it is finite volume, then you discretize it with a number of control volumes, non-overlapping control volumes. After that, you choose the governing equation, discretize it, and the discretized set of equation needs to be solved with the help of some boundary conditions. So boundary condition is important. We have also seen the types of boundary conditions, and in numerical simulation, CFD, numerical error is very important. So we have also discussed that what is truncation error, what is round off error. So little bit of discussion we have done. So this is the presentation slides of last class. So we started finite volume method. It starts from the integral form of the governing equations, and then you need to basically integrate the differential form of the equation over that domain, over that control volume. And how a control volume is represented, that is, the central point is P and its neighboring points are east, west, north, south, like that. In how it can be represented, we have seen with the help of a very simple equation, a heat conduction equation. Now as I told you that starting, if I start the solution method with the Navier-Stokes equation, it will be difficult to understand. So we choose this very simple equation, which is a steady state heat conduction equation, probably the most simplest form of PDEs, that is a second order PD only, and that we have taken as an example, and we have tried to discuss that how the process, the numerical process can goes on. Okay, so this is, we took an example of a rod and we discretized it, then we have written it in this form. We do some so here actually one dimensional heat conduction in a rod problem was taken, and then these were the dimension and boundary conditions, and then we have discretized it, we have written it in the form of an algebraic equation like this, and if we solve it with the help of Gauss elimination or Gauss-Seidel or any other method or Thomas algorithm, then you will get the final solutions. And this is all about numerical errors, and we know that how it can be optimized, step size can be determined from this competition of these two type of errors. So that part also we have discussed, and we also have seen that how grid independence test can be performed to find out the maximum possible step size without compromising the accuracy of the solution. Okay, so that we have also discussed, and up to this point we covered in last class. Now let us start today's part. That is, it will be lecture 5. So I will just 1 minute. Yes, I hope now it will be visible to you. This is the outline of the course. Once more, you see that we started from this introduction of CFD, then idea about governing equation, discretization methods, then finite volume method, and introduction to ANSYS fluent. We also spent one dedicated lecture for starting for doing some case study in ANSYS fluent. What are the steps? And I have shared with you a tutorial videos. If you have practiced, then you can get an insight definitely. And so this is the thing that we have covered. Now we will go to this fifth one, and fifth one is all about about discussion of some elements of CFD solver, and we will start with this thing, this unsteady state equation and some elements of CFD solver. Under this heading we will start today's lecture, and if you have any queries or doubt by this time, you can feel free to ask me at this stage or at any point of time. Okay, so the major thing that I like to see here, that today's our coverage will be an unsteady state equation. Okay, so this is important. So far we were only handling the steady state part. Okay, because the equation, heat conduction equation that we have taken was like this: K into del 2T del x square, if there is a source term like this, equal to 0. Or sometimes we have not considered the source term also, only we have taken k dt to dx square equal to 0. So this equation we have solved with the help of finite difference and finite element method, and this equation signifies what? That this is steady state equation. That means no temporal term is there. Okay, the temporal term means what? You should have a dt by dt. D means this small t denotes actually time, and this capital T denotes temperature. So with respect to time, how temperature will vary, so that term is known as temporal term. In Navier-Stokes also, in the left hand side you will see that first term will be this temporal term, that is the unsteady state term. If there is steady state term, then we generally neglect it. Okay, so for simplicity we are so far considering the steady state problem, steady state equation. Okay, steady state. Now we will see that how unsteady problem can be taken up. So that we need to first see, because this is very important. In practical application you will encounter a number of unsteady state problems. So let us start that part with the example of again one transient 1D problem. So transient means basically unsteady problem. Okay, where the temporal term will be active, you cannot neglect it, means something is changing with time. So in many book you will find these are unsteady 1D problem or transient 1D problem. And again for simplicity we will consider the heat conduction equation only. Okay, so without considering any convection, we just consider that how heat conduction is taking place, but in an unsteady manner. So the problem that we are going to choose here is like this. You have is someone is waiting, I think, in the lobby. Let me allow. Okay, it is fine. Nobody is there. Okay, so the problem, example problem that we will take today is like this. You have a plate. That plate has a thickness like this, 2L. Okay, so this has a thickness. This one is 2L, and this is in x direction, and in y direction the size is infinite. Okay, size is infinite means it has very long distance, so that we can neglect the variation in the y direction or vertical direction to make the assumption that this is only a 1D plate. 1D plate means temperature variation is taking place only in x direction. So what if the problem states that you have a plate, hot plate like this, which has an initial temperature Ti at all the points. This Tx0 means Tx0 means T is a function of space and time, and at 0 means at the very initial moment it has temperature Ti. So initially all the point has Ti temperature of this plate. Now you are submerging this plate into another fluid domain, it may be gas or liquid, where the surrounding temperature is T infinity. So your plate is at initial Ti temperature at all the points, you are keeping it into a second fluid medium where the surrounding temperature is T infinity. So if I consider that Ti is greater than T infinity, then cooling will take place, right? The hot plate will gradually cool down by exchanging heat with the surrounding, and heat, we consider that heat transfer coefficient is very large. Okay, so that very cooling will take place, and determine the temperature of the plate as a function of space and time. This is important. Earlier in last classes, what we were doing, we have a rod, for example, like this, and we told you that at one end of the rod is, let's say, 100 degree centigrade, and another end is, let's say, 200 degree centigrade. Then our problem was that at steady state, what will be the temperature distribution? How the temperature will vary from each of the points of this rod. Okay, so that is at a steady state. Now we are invoking the unsteady term. That means we need to reach the steady state finally, but along with the time. Okay, so how from T equal to 0 to as T progresses, the temperature will change at each time step, that we have to know. So for example, T equal to 0, we know that all the points will be having a temperature of Ti, T equal to Ti. Okay, now we need to know at T equal to delta T, after time delta T, what would be the points. So for all these points that you need to know. Okay, so then after T equal to 2 delta T, you need to know. So along with the spatial variation, you need to know the temporal variations with respect to time. So each time step, so in these cases what you have to do, so you are starting from T equal to 0, then in the next step T equal to delta T, after delta T time step, you need to see the how will be the temperature distribution of this plate. Okay, that you have to calculate. Then after T, that means after reaching this delta T, you need to solve the spatial derivative terms. So at each point you have to calculate the temperatures. Okay, then after T equal to delta T, again you solve the spatial, whatever we have done earlier, that you have to solve. So time wise the temperature profile will change in this case. Okay, now we will see that how this problem can be approached, and we will take the route of finite difference method for your easy understanding. Okay, but it can be done in a finite volume also, there is no issue. So if now first you see two things. Okay, so what we told you that the approach of CFD, what means steps of CFDs are that the first step is to identify the geometry, right? So here geometry is given to you. So this is the geometry. Now the moment geometry is given, you try to look into it and find out if there is any symmetry in this figure. Okay, because it is not always necessary to compute the entire domain. Okay, because that is not necessary, unnecessary. You should not increase the computational time. So you see, this is a system where both the ends, because in y direction we are not considering any variation, change is taking place only in x direction. And you see this line along this vertical line, you see that these are mirror image basically. So if I consider this L distance here, so this part is basically a mirror image of this part, right? So if I can solve one half of it, half of the domain, then rest is only the mirror image. You can just plot it, right? So we need not solve the entire domain because it is not needed. The whatever result you temperature you will get at this point, at the equal distance from the center line, you will get the similar temperature. So first step from the geometry, you need to understand if there is any symmetry based on the boundary condition and geometry profile. So if you find out some symmetry, you can solve only that domain. So in this particular case, we will not solve this entire 2L length, we will just solve this one half of it and rest will be just a mirror image of it. Now the thing is that you need to now find out a boundary condition at this point, at this midpoint. Okay, so at this x equal to L, we need to find out a boundary condition. So you see both the boundary condition are at t equals to t infinity, right? And so what will be the profile since your t infinity is cooler than the internal temperature? So if I plot along this x direction, the temperature profile may go like this. Okay, so here it is T infinity, here it is T infinity. So it will pass through a maxima at the central line. Okay, so at the central line there will be a maxima, right? So this kind of profile. So I will get a profile like this since this inside temperature is high. Now at the maxima, what will happen? Delta T, delta X will be equal to 0. Gradient of the temperature will be 0, right? So since I am interested to solve only half of the domain, I need a boundary condition here at the central line. So I can tell that my extra boundary condition at x equal to L should be delta T delta X will be equal to 0. Temperature gradient will be 0. So this boundary condition I can take. So my here my t is equal to T infinity, and here T equals to dt as here temperature means this is a Neumann type of boundary condition, dt dx equal to 0. So here Dirichlet boundary condition, here Neumann boundary condition. Okay, so now let us go to the next step, find it out. So this is the geometry that we are just looking for. Now one side at t equals to T infinity and other side the boundary condition is dt dx equal to 0. So this sign is given in order to indicate that symmetry is there. So other half will be just mirror image of it. So we will solve this part, and initial condition is that at t time equal to 0, all the points are at Ti. Okay, at a particular the temperature is given there. Okay, so this is the geometry part. Then CFD steps, you remember the first step is to the finding out the geometry and symmetry, etc. If any student organizer is there, please accept if anyone is joining new. I am not going to that window. So
Okay,
this
sir.
okay. So this is geometry part, and second part is what? Second part I told you that second part is to identify the governing equation. Okay, finalize. You have to finalize the governing equation, and along with geometry we have also specified the boundary condition, which is also needed, that we have fixed. Now we need to concentrate on the governing equation. The governing equation is written here in non-dimensional form. So generally in such case what will happen, uh, the the equation ideally should be dt by d small t will be equal to some alpha, which is known as thermal diffusivity, as you know, and delta 2 t delta x square. So in dimension form, in normal form, it should, the equation is like this. So earlier we were just considering this one 0 for steady state applications, and we were solving the equation. Now this is not 0. Okay, so we need to keep this part. So this equation we need to solve, but here in this case we will follow this equation in a non-dimensional form. Okay, so why non-dimensional form? Because you will see mathematically that if you use any equation in non-dimensional form, then it has certain advantages. Okay, so because number of variables will be less. Just 1 minute. हाँ दिवाकर जी, हाँ 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 अभी भेजता हूँ, कल रात को ही मुझे सब डॉक्यूमेंट मिला उसका, तो आज ही भेज देता हूँ। ठीक, अभी 1 घंटे में, हाँ 1 डेढ़ घंटे में भेज देता हूँ। ठीक है, अभी श्योर 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 श्योर, ओके। Sorry, am I audible? Hello?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay, 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 good. So now you see that if I pose any different, any governing equation in engineering system, in engineering science, you would see that in many subjects, heat transfer, mass transfer, fluid mechanics, thermodynamics, in many format we use a non-dimensional form, because it gives some advantage, because your variable number reduces. At the same time, if you think of any scale up, etc., these non-dimensional parameters help us. Okay, so that's why if possible we will always try to make it non-dimensional. So here also this equation is formulated in a non-dimensional form like this. So instead of directly writing temperature, we are writing theta, and this is del theta del tau is equal to delta 2 theta delta x square, where the theta is defined in this way. The numerator is T minus T infinity. The T means not temperature at any time step, and T infinity is the surrounding temperature, and at the bottom Ti minus T infinity. Ti means the initial temperature minus T infinity. So this is how this theta is defined, and x, that is the length parameter, that is defined making dimensionalized as small x by L, where small x is the distance and L is the total distance of my domain, and this tau is given by alpha t by L square. Now if you substitute these values in this particular equation, so you will get back this equation. Okay, so in order to take the help of non-dimensionality, we are just making the equation or simplifying the equation in this format, because this has some mathematical advantage. So my governing equation is right now this one, d tau d theta d tau will is equal to delta 2 theta by delta x square. Okay, so this is a second order differential equation, and I need to now solve it. So what we did, we have defined geometry, then we have defined governing equation, and now we need to also declare the boundary conditions. Anyone? Sorry, if there is anyone is not saying anything, please mute it. Okay, so now we will see what are the boundary conditions here. So it is not only boundary value problem, it is also an initial value problem because time parameter is there. So the initial and boundary conditions are like this, based on this non-dimensional form. This tau equal to 0, initial condition tau equal to 0, means at tau equal to 0, the theta equal to 1, tau equal to means tau equal to 1 means at t equal to 0. If t you put t equal to 0, then your tau will be equal to 0. That will give you initial condition, and at that condition theta equal to 1 for all x. So all points will be theta equal to 1. That means this t will be ti at initially, right? So ti minus t infinity by ti minus t infinity. So theta will be equal to 1 for all x. That is the initial condition. And for tau greater than 0, first boundary condition is that at x equal to 0, x equal to 0 means is this left hand side, because x equal to 0 by L will be 0. So capital X 0 will be theta equal to 0, because at that point you have this theta equal to 0 means what? This T infinity. Okay, because here the temperature is T infinity, so T infinity minus T infinity, so it will be 0. So at x equal to 0, theta equal to 0, and second boundary condition is that at x equal to 1, you have this delta t delta x equal to 0. So that if you transform in this format, so it will give you delta theta delta x equal to 0. Okay, so this we have explained in the last slide. So you have seen that how this boundary condition we are getting. So if you dimensionalize it, then you will get delta 3 delta x equal. So these are my boundary condition. So my geometry declaration is done, my governing equation and boundary condition specification is done. So what will be the next step? Anyone? Can anyone tell me what will be the next step of CFD for solving this?
So we have to generate the elements.
Yes, right. Your discretization. So next step will be all about discretization. Now discretization in two sense. One is domain discretization. Domain means this geometric means entire domain has to be discretized into a number of points, and since we are considering only one dimensional problem, so we'll, if it is finite difference, we will consider only some points, right? 1 2 3 4 like that. And if it is 2D, then means if there was variation in y direction, then we have to take a grid like this. So along with this x, there will be some y directional gridding will be there. See, this is called domain discretization. Another one is called equation discretization. Okay, so equation discretization means you have to convert this differential equation to a set of algebraic equations. So these two things will be done, and for that we need to choose a method, either finite difference or finite volume or finite element. Now here in this particular problem, let us first see the finite difference method, because that is easy to understand. So now let us come to the discretization step. So here is the domain discretization, the figure you see. So we are considering equally spaced grid point in x direction. So first point, so since we are making it a non-dimensional right now, so your x is basically capital X will be x by L, right? So at this right hand side, this will be 1, right? This x will be equal to 1, because that will be L by L equal to 1. So here it is 1 and here it is 0 at x equal to 0. So this is the first point, second point, and for simplicity let us take this much 5 points only. Okay, so the first point is at this 0, is marked by 0, second one is 1, this is 2, this is 3, this is 4. So in finite difference algorithm, we are just decomposing this domain into 5 points only, marked as 0 1 2 3 4. Okay, so these 5 points are there where we need to write the equation, discretized equations at each points. So these 5 points indicate that you will get 4 or 5 number of equations, a linear algebraic equation that has to be solved simultaneously. So why 4 I am stating? Because in this particular point the value is known. Your Dirichlet boundary condition is given at the left hand side. So this point we know the variable temperature is known here. and others are unknown. So T1, T2, T3, T4, these four is unknown, unknown. So we need 4 equations. We need to write the governing equation at these 4 different points. Okay, so let us first apply the knowledge that we have learnt in the last class, that how spatial terms can be discretized. Now, what do you mean by spatial? And this term is known as spatial term, and this term is known as temporal term. So we have in the last class seen that how spatial discretization can be done. We have elaborated that part. So first let us do that thing what we know already. So that is why the left hand side we are keeping it is as it is for the time being, delta theta delta t equal to, we are using here central difference scheme. Okay, so if you remember, for discretizing a second order derivative using finite difference method, you can either take forward difference, backward difference, or central difference, and central difference gives certain advantage because it is one order accurate, more accurate. So so what the equation, let me write it, delta 2 delta tau, and this is delta theta delta x square. So this was our governing equation. So what I am doing, this second order differential term I am discretizing with the help of this one, which is a central difference scheme, CDS. Okay. So what is central difference? You have to go back to the last class. Okay. So you can write this second order term in this way, right, in a general for any particular point I, irrespective of the nature of the point. So for any ith point you can write it. So the equation for x equal to 1 is obtained by using image point technique, that is substituted by theta m plus 1 equal to m minus 1. Now this is an important technique, let me spend some time here, because at this very left hand Dirichlet boundary condition is given, your value is given here, okay, specific, but here we do not, the value is not directly given, rather delta theta delta x equal to 0, that part is given. Okay, so this is the only the Neumann type of boundary condition. So this is given, not the precise value is given. So what is assumed here, that we will, if you like to determine this value, this gradient, you should have a value here, because then only gradient at this point can be obtained if I know some value immediately after that, but that is not available to us. So what we consider, that we consider an image point of these 3 here and consider it as a point number 5. This is an fictitious point. Okay, arbitrary point, this 5 point we will consider, which should be an image point of this 3, this 5 is here, and we will consider that whatever temperature is having at this 3 point will be having the same temperature at this 5. So let's say if here the temperature is let me write it in theta terms. So it is, if it is theta 3 and let the temperature is theta 5, we will consider this theta 3 will be equal to theta 5, because the gradient is 0 here. Because the gradient is 0 means what? If at any point, let's say you have 2 points here, and any variable that is varying between these 2 points has a gradient here 0 at this point, that means it is either varying in this manner or in this manner. So at this particular point you have a maxima or minima. Okay, so that's why this here it will be delta t delta x equal to 0. So considering that concept, we are taking a image point here as a 5, it is a fictitious point, to get the value of this delta theta delta x. Okay. So now since with this gradient is 0, we can consider theta 3 will be equal to theta 5. So that is here written, that if theta m plus 1 will be equal to theta m minus 1. And if you take these assumptions, then you can substitute this theta m plus 1 with theta m minus 1. And if you do that, then you can write this for the delta theta m by delta t equal to 2 theta m minus 1 minus 2 theta m by delta x square. So look, my 5 point is gone now, gone from here. We are expressing the boundary condition with the help of some points at points of the function at the value this and this point. Okay, so that is how for the extreme right hand side thus delta theta m by delta tau term can be discretized. 2 theta m minus 1 basically, if I write it you can understand in this way. Delta theta m delta tau can be written as theta m minus 1 minus 2 theta m plus theta theta m plus 1 by delta delta x square. Okay, so this is how you can write it. Now this is called central difference scheme, because I am discretizing this one using central difference scheme. Now at this m plus 1 point is a fictitious point, but which is equal to this theta m minus 1. That is why we are writing it, because m plus 1 equal to m minus 1. So 2 theta m minus 1 minus 2 theta m by delta x square. Okay, so this is how this equation, the governing equation at the right hand side point boundary can be written. So let us consider one of the equation, and all other points it can be very straightforwardly written as this one, or means at I equal to 0 this point is known to us, and this we have already written. Now all these other points, these 1 2 3 points, we can write this one delta theta delta 1 will be equal to simply 1 by delta x square theta 0. So this is using central difference scheme. CDS scheme if we for adopt, then for I equal to 1 you will get I equal to 2 points, you will get this one. I equal to 3 point, you will get this one, and I equal to 4 that we have just in the written in the last slide. So this equation we will get. So I need these 4 points unknown to me. Okay, so 4 unknown points, and I am getting 4 equations, 1 2 3 4. Okay, so 4 equations, 4 unknown, but all these are right now what, some ordinary differential equation or ordinary differential equation of initial value problem type. Okay, because this left hand side we are having delta theta delta t term, delta tau term is there still now existing, and initial condition is known to us that at t equal to 0 at all the points theta will be equal to 1, that is known to us. Now this is for initial ordinary differential equation, and we have discretized the right hand side only. Special term we have discretized so far, and this part we have done in the earlier class also. Now we need to see that how this temporal derivative, means temporal term, the left hand term, how this can be discretized, because we have not learned it yet. We know that how spatial terms can be discretized with the help of forward difference, backward difference or central difference, but this left hand term we do not know yet that how we can discretize this one. So that we will see now that how this can be done. So for solving such equations, such ordinary differential equations, we have 3 approaches. One is known as Euler method or explicit method. Second one is known as Crank-Nicolson method, and third one is known as pure implicit method. Okay, so these 3 different methods are available to us for discretizing these terms. Okay, so we will see one by one how these methods work. So I just showing you some snapshot of a book. I will give you reference of this book. Due to shortage of time I could not convert them to proper PowerPoint slides, but I hope you can understand this thing. So let us very closely see that I have now a term called delta theta delta t, which I need to discretize. Okay, and we have to discretize with the help of finite difference. So since the present problem is an initial value problem, we will know the solution of tau p at some point in time tau p, and we will be seeking uh, at theta p plus 1 at some later point tau p plus 1, which is equal to tau p plus delta t. So, means what it means to say that you know at initially the value at this superscript indicates that the time part. Okay. For example, we were writing in earlier case like theta 2, theta 3. So, this 2, 3 indicates what? The position of the space, spatial position, right. Now, whenever time temporal parameter is there, along we cannot sorry, these are subscript represents spatial positions. So, we will put some superscript here. Superscript indicates the temporal term. This is indicating temporal term and these are indicating spatial term. So, this is a common convention. So, if I write theta 3 and p plus 1, that means the value of theta at third point at a time interval p plus 1, like that. Okay. So, that is the common convention. So, what it states that since it is an initial value problem, because initial point you know, that means at tau p you know theta equal to some value, let us say it is having some 5 value, arbitrary value. Then you need to find out in the next time step at tau p plus 1 what should be the value of theta, right. So how to do get these things? So, we can extrapolate it. Okay. So, that extrapolation can be done with this one, with an assumption like this, that theta p plus 1 will be equal to theta p, that is the value of theta at pth interval, plus the gradient, that is d theta d tau at p into delta t, if delta t is the time step. Okay. So, this p plus 1 means here we like to see that p plus delta t time step, right. So, that is why it is said in the Euler method of solution, the solution at a future time tau p plus 1 is obtained by computing the derivative at present time tau p and then moving ahead in time in the following way. So, theta p plus 1 will be equal to theta p into the derivative means gradient d theta d tau at p into delta t. Okay. So, we know that there are many functions. This is a basically Taylor series type of expansion, that if you like to know the value of the function at a particular point, if the earlier points are known, you can write it in this way, provided this gradient is known to you, d theta d tau is known to you. Now, at what point this d theta d tau you will take, that is the matter of questions. So, here we are assuming in Euler method or explicit method that this theta p plus 1 will be calculated based on the derivative at pth value, at pth point. So, this is, so you see that your p plus 1 term is explicitly expressed with the values of p. So, here all the p's are here. Okay. So, this is why this is called explicit method. Now, there is another process which is called implicit method. So, there what can be done, p plus 1, I can write it theta p plus d theta by d tau, instead of taking p I can take it p plus 1 into delta tau. So, that is also possible. So, this derivative term, instead of taking this earlier point, I can take the forward point also. So, here you see that this p plus 1 is not explicitly defined with p. So, you have a p plus 1 term here, and so this is known as implicit method. Okay. So, this is another scheme, and there may be another case where you can ask question that why should we take this derivative at pth point and p plus 1 point. I can take an average of p and p plus 1. So, in that case what will be the case, this theta p plus 1 will be equal to theta p plus I can take half of d theta d tau at p plus d theta d tau at p plus 1 into delta tau. So this is also possibility that instead of here in Euler explicit method we are taking the gradient at pth value, in implicit method we are getting it at the p plus 1th value, and there is another possibility we can take average of this p plus 1 and p value, that is also, this is called Crank-Nicolson method. This is Crank-Nicolson method, this is implicit method, and this is explicit method. Okay, so these three mechanisms are there. How now you consider any one of them and you can express this d theta d tau in terms of theta p plus 1 or p. Okay, so for Euler method, so what we are, so if geometrically you like to see, let us see this graph. So it states that you are plotting theta versus tau, because you are interested to calculate d theta d tau. So let us, this linear progression is taking place in this along this curve. So this is at point is theta p, this is theta p plus 1, right? So what we like to know here, that you are trying to calculate this theta p plus 1 from the values of this theta p, and we are taking a linear extrapolation. Okay, this is the Euler method, because you are taking this point and taking a linear extrapolation to predict the point at theta p plus 1. So in implicit method the reverse is true, you are trying to get the value uh, of this p plus 1 from the derivative at this particular point, and you can also take an average in the Crank-Nicolson method. Okay, so these three methods are there to discretize the temporal derivative. Now let us see the Euler scheme. If we follow, we can write it that, and I have 4 points. If you remember the geometry, I have a domain like this where I have point 1, 2, 3 and 4. Okay, so 4 points are there, 1, 2, 3, 4. So here I can write this is theta 1, this is theta 2, this is theta 3, this is theta 4. So I can write for theta 1, following this Euler scheme, theta 1 theta p plus 1 will be equal to theta p 1 plus d theta 1 d tau at p into delta tau. So this is for point 1. Then for point 2 I can get this one, and for point 3 I can get this one, and point 4 I can get this one. Okay, so I have 4 equations, right? So if you go to the earlier, sorry, so I have 4 for this I equal to 1 2 3 4. I have this 4th term I need to discretize, right? Theta 1 2. So that we can do with the help of these 4 equations. Now next step is what? You write this equal to theta p theta 1 p plus 1 minus theta 1 p by delta tau. That's how you can express this part. Okay, so let us see that. So what we are doing, we are directly just if it is equation number 1, this is equation number 2, this is 3, this is 4, then we can come here, we can just take express this part, theta 1 p plus 1 minus theta p by delta t, and whatever is remaining in the right hand side, my governing equation that we have already done it, that we are keeping as it is. This is equation 1. So actually the whole equation is being derived. So equation 1 is this one, d theta 1 by d tau, and we have discretized it in this way, 1 by delta x square into minus 2 theta 1 plus theta 2, right? This is my equation number 1. Now I am writing this left hand side also using Euler scheme, theta 1 p plus 1 by minus theta 1 p by delta t. So this is my equation number 1 and fully discretized. No differential term is there. This is a algebraic equation now. So this is for I equal to 1. Similarly, this is for I equal to 2, and this is for I equal to 3, and this is for I equal to 4. Okay, so these 4 algebraic equations we got now, simultaneous algebraic equations that we are getting. Okay, so if you can solve them, now our problem is solved, because there is both the temporal term and spatial term is discretized now. Now these 4 equations, if you see that if I take express all of them, in the left hand side we can keep the p plus 1th term, and right hand side we can keep pth term. then the equation can be rearranged in this set. Okay, and if you express them in matrix form, it will be like this: theta 1, theta 2, theta 3, theta 4 at p plus 1th term. So this is the left hand side, and right hand side you can write in this way, because all of them are associated with theta 1, theta 2, theta 3, theta 4 at pth time, and we can express this r equal to delta tau by delta x square, because that is a very common term. Then you can simply write 1 minus 2r into r. So this is the tridiagonal matrix is being formed here. Now here the advantage is that, advantage you look into it, you need, because these values are known. Okay, so at pth time you know, because initial value problem, so you can know these pth values at pth interval. So if these are known, then you can just directly multiply it, because these two r will be having some value, and if you multiply it, you can directly get the value of theta p plus 1 time interval. So you need not solve a set of algebraic equations. So you need not follow Gauss elimination, Thomas algorithm, etc. You just do some matrix multiplication, which can be easily done in computational, in a code, in a computer code. And that's why in the computing lab classes you are taught how to do matrix multiplication and all these things. So if you do this matrix multiplication, you can directly get the results. You need not go for any solution methods. Okay, so that is the advantage of Euler method. Okay, because you need not solve a set of algebraic equations. But there is a limitation. Limitation is that, you know that for getting any numerical solution of any tridiagonal matrix like this, your diagonal elements should be dominant, right, in order to get a stable solution. Okay, in order to get a stable solution, these diagonal elements should be dominated and it should not be negative. So this 1 minus 2r should not be negative, so that gives a restriction that your r should be less than 0.5. If it is greater than 0.5, then what will happen? The diagonal element will be negative at some point, and if any matrix have the diagonal element negative, then the solution, numerical solution, will be unstable in nature. Okay, so this will give you some unstable nature to the solution if you take more than r more 0.5. That means what? The moment you are giving some limit to the value of this r, so this r is basically delta tau and delta x square. That means you cannot take any arbitrary value of delta t or delta x. So you need to choose. So once your spatial gridding is fixed, your delta x is fixed, right? So the moment I divide it into 5 points in the domain, the x delta x size is specified. Now this delta x, if it is fixed, you cannot take any arbitrary delta t now. Now you need to choose such a value so that the r value remains less than 0.5. So this is called stability criteria. Okay, so stability criteria. Now this is just to simply understand the stability concept, but numerical stability concept. But there are so many special type of stability criteria are available, like von Neumann stability criteria. Then there is CFL stability criteria. So these are different specific stability criteria which was proposed by the numerical scientist. Okay, so they have given that if you follow this, then your system will be more stable in nature. Okay, let me go to the next part. So this I have explained, this text part is written. If you read it later on, it will be clear that why it should be less than equal to 0.5. Now let us come to the Crank-Nicolson part. As I was pointing out that Crank-Nicolson, here theta p plus 1 is expressed as theta p plus half of this average p and p plus 1th term average. So in Euler what we did? In Euler theta p plus 1 was expressed as theta p plus your d theta d tau, that was calculated at p into delta tau. So this is what we have calculated. This x, why it is explicit called? Because your p plus 1th term is explicitly described in terms of p. Okay, but here we are not considering this part. Instead, we are taking an average of the pth average of the derivative at pth level and p plus 1th level and taking an average of it. Okay, so this is the difference, and this makes this is now no more explicit, because in the right hand side also p plus 1, in the left hand side also p plus 1. So this is now a different case. Okay, now if from this one again you can substitute this part into our governing equations, then you will get the equations in this particular form. Okay, so right hand side we have already discretized, and left hand side you can now pose it, because you can get from here, you can write theta p plus 1 minus theta p by delta tau, uh, that will be equal to this part. Okay, and if you uh, put all these values, then then 4 equation will again be like this. Okay, and if you do little bit of algebraic manipulation, then you will see that you can present that matrix again in this form. Okay, so earlier this part was not there, means up to this in case of Euler method we were getting this part. Okay, but since you are now taking the derivative as an average of 2 points, your this left hand side matrix is coming. Now this right hand part is known, this p value is known, and if you fix a value of r based on the delta x and delta tau value, then this right hand side will be known to you, but still you are getting a matrix like Ax equal to b. Okay, now this is a set of algebraic equation. So now you need to take the root of Gauss elimination or Thomas algorithm or any other method. Okay, so in Euler method the advantage is that you are going to you do not need to solve a set of algebraic equation, you just do matrix multiplication and you will get the answer. But in Crank-Nicolson you need to solve a set of linear algebraic equation in the form of Ax equal to b. Okay, but here advantage is that this is sometimes this is called unconditionally stable, because you have here unconditionally stable means you can take any value of delta t. Earlier there was a restriction that delta t by delta x 1 by delta x should be less than 0.5, like that. So here, although it is unconditionally stable, means you can take any value of delta t, because here your possibility is only 1 plus r, no negative sign is there, so you can take any value. But if you take a very large value of delta t, sometimes it gives numerical error. Okay, means some error you can encounter. Okay, so that comes from the some other sort of instability that will arise, and this stability part is a broad topic, it needs a little detailed elaboration. In the short course I am not going to cover it, but you remember that if you take even delta t a large value in Crank-Nicolson method, there is possibility that you will get an error. Okay, numerical error. Now the third point, that is pure implicit method. As I told you, this is here this derivative is expressed purely implicitly in p plus 1th level, uh, and if you again put the values in our governing equation, these will be the 4 set of equations. And again, if you organize little bit, you are going to get a matrix like this, Ax equal to b. So here also again you need to solve a set of algebraic equations, set of linear algebraic equations, because you know this part, but this is your unknown, and you see that you have 1 plus 2 are terms in all the terms. So again there is no question of instability here, and this is called unconditionally stable. Okay, and there is no condition for stability, unconditionally stable. Okay, so here in this case of implicit method, you can take a large value of delta t. So large value of delta t means you can at a very shorter time you can finish your computation. Okay, without any unstable situation. So delta t can take a large value of delta t can be taken. Now if all the three methods, if we compare, you will see that this your explicit method or Euler method is basically forward in time and central in space. Okay, so we read it central scheme, central difference like this. So if we go to the explicit part, so you see that this is the difference. Sorry. This is the Euler part. So you see that this is forward in time. Forward in time means this left hand side, if you look into it, it is a forward difference operator. Okay, so delta t delta tau you are expressing as p plus 1 minus p by delta t. So this is a forward difference, and this is delta x square means central in space. So spatial derivative is central space and temporal derivative is forward derivative. So it is called FTCS scheme. Okay, so Euler method is known as FTCS. This is forward time and central space. Forward time and central space, FTCS scheme. And its order of accuracy is that since you are using central in central difference space, and if you recall that central space is one order more accurate, second order more accurate. So your order of accuracy in terms of space is second order, and in terms of time is first order, because you are using forward derivative in for the temporal term. But Crank-Nicholson is both delta x square delta t square, means it is central time central space. So if we pose those equation and elaborate it, it can be shown that your you can let us go see once more that this is and this part. So this is Crank-Nicholson part. So you see here that here central time and central space, both things will be taken, but you cannot understand it from this form of equations. You need to go one step high, so that you can take into the p plus 1th also in the left hand side. Then only you can understand that part. So that part is missing. Otherwise, if you write it, elaborate it, you can understand that Crank-Nicholson is central time and central space. And this pure implicit scheme is backward time and central space. So here also delta x square, in terms of space all three are second order accurate. In terms of time, this pure implicit and pure explicit is delta one order first order accurate, but Crank-Nicholson is second order accurate. So since accuracy is more in case of Crank-Nicholson, this can many times this is a preference, method of preference. But again, if you like to write your code, then only the first Euler method will be advantageous for you. So now let us look into the advantage and disadvantages for this each of these three methods. So Euler method is what? Advantage is simple, no simultaneous equation to solve, and easy to program on computer. So these are the advantages. And disadvantage is that it is conditionally stable. So you need to very carefully choose the value of delta t with respect to delta x, so that the r should not be less than 0.5. Okay, so this will be the condition. Then restriction on time step due to the stability limit, and thus making the computation slow. So you have to take a very small value of delta t only in order to satisfy this thing. Pure implicit is what? Advantage is that unconditionally stable method, no restriction on time step. And disadvantage is that a set of simultaneous equation to be solved in each time step, hence more computational effort and difficult to program on a computer. So if you like to go for programming, you will see that it is not so easy. Then comes the Crank-Nicholson part. So it is more accurate than Euler and the pure implicit method for the same time step. So as you have seen, this is central time and central space. It has one order more accuracy. It is stable. Initial instability may arise for large time steps, but eventually they will damp out. So that is the advantage. And disadvantage is that a set of, again, a simultaneous equation needs to be solved for each time step, and hence more computational effort, difficult to program on a computer. So so these are the different three schemes or three methods for solving the unsteady state problem. Okay, so here instability will come. Here you need to choose a particular scheme, either Euler or pure implicit or Crank-Nicholson. and you need to go for it. So this is all about that how unsteady equations can be solved, that is now shown. So let me once again quickly go back and understand that what was our target. So we tried to solve a set of equation like this, an algebraic equation and a transient 1D problem like this, that you have a domain and you have a governing equation like this. Now we learned how to discretize the spatial term in the last class. Today these three methods can be adopted to discretize this part, and all these three method have some advantages and disadvantages, and if you follow them you can get all the results. Okay, so this is how an unsteady problem can be solved. Share again these slides with you, and you must and I will refer the book. If you can collect it, you can read the book also, but this is the approach how the temporal term can be derived. Okay, now yes, this is the part of the book that how to choose a particular method. Okay, so you may ask that what method to choose. So again, there is no hard and fast guide for that. Okay, it depends on the situation and what kind of problem you are handling, and you can need then what is your need. This based on you need to take the decision. So if I read these few lines, the answer is not so straightforward, because the final choice depends on the accuracy requirement of the problem, whether the solution at earlier or later times is desired, and the speed of the memory of the computer. For example, if the solution at an earlier time is required and accuracy can be compromised, the Euler method should be preferred. On the other hand, if the entire temperature history is the one sought, then either Crank-Nicolson or pure implicit can be used depending on accuracy requirement. For larger time step, pure implicit scheme is better than Crank-Nicolson, as over a larger interval the steep rise or fall in the beginning followed by a flat tail is more realistic as compared to linear profile throughout. For small time interval, however, Crank-Nicolson scheme is physically more sound. Okay, so this is you need to take the decision that which method to follow. It depends on so many factors. So if you start working in this domain, then you can gradually understand that which method to take up. Now consistency, there is another important term like stability. In this method we learned one thing which is called stability of the numerical solution. So there are stability criteria, etc., because if you like to make the system stable, your diagonal elements of the matrix, coefficient matrix, should be dominated. It should not have any negative value. Okay, so that gives a stability concept, and another concept is consistency. So it states that a finite difference procedure is consistent if it approximates the solution of PDE under study and not the solution of some other PDE. For example, consider the solution of one-dimensional transient heat conduction problem by explicit method or Euler method. We know that truncation error of Euler method is delta t delta x, forward time and central space. Since the truncation error tends to 0 as delta t delta x tends to 0, the explicit representation is inconsistent with the original PDE. Okay, so actually original PDE means this is the differential equation. In numerics, what we are doing, because PD is the differential equation. Differential equation is applicable only for continuous function, but in numerically what we are doing, we are dividing it the space. This is no more continuous in nature. Okay, so you need to choose those points in such an interval so that your consistency is maintained. Okay, so this is another part which you need to remember during solving the things, solving such equations. So now I will show you, we have just seen a one-dimensional unsteady or transient state equation, the heat transfer equation. Okay, so if it is 2D, okay, instead of 1D, if you have y direction also, the governing equation will be like this. And if you discretize it, okay, in Euler's explicit method, then this will be the form, and you have from the stability criteria you have a restriction like this. Okay, and if you use pure implicit scheme, then your equations will be looking like this. You see that here on the right hand side is all p value, but here it is a mixture of it is p plus 1 in pure implicit scheme. And if you take Crank-Nicholson, you will see also p, a combination of p and p plus 1. So here also the r comes like this. This is the r, and the value of r will again impose some stability criteria in this controller. So this is a two-dimensional problem. So we have shown you how to solve 1D. So this is how 2D can be discretized, 2D equation. Now this is the 3D form. Okay, so this is from 2D to 3D. If you go, so this is one equation, this is another equation. No, so this is the following, and so there is some other schemes are there. ADI scheme, like alternating direction, direction implementation scheme. So that I am not going to cover, because this ADI scheme etc. will help you to get advantage of stability etc. Little bit detail. It can be understood only if you can start working on this particular area. But I like to show you that how a 3D conduction equation, unsteady conduction equation after discretization will look like. Okay, so this 3D, this is a 3D differential equation, and you see that now it is a pure algebraic equation. Okay, now you have to solve it taking any particular method. Now I will come to some other important aspect, elements of CFD, that is the computational grid. So computational grid, here I like to give you two concepts, that is structured grid and unstructured grid. So as I told you, that first step of a CFD is to define the geometry, right? And then you have to discretize it. Now discretize can be done either in a structured grids, means you use a single type of elements. These are called elements, means you see that rectangulars or rectangular in 2D, it is rectangular shapes are there. Okay, so I can so for this particular domain you can use that only one type of grids are being used, and I can number it easily 1 2 3 4 etc. So these are called structured grids. Okay, so as you see, so its aspect ratio may change from due to accommodating the geometry, but you will see that all are basically rectangular shape. Okay, and you can very precisely number them in the form of I, J etc. indices. But another set of gridding exists, which is called unstructured grid, where you see that some are triangular in nature. This is a triangular grid, and you see this is a rectangular grid. So there is a mixture of different types of grids are there, and these are called unstructured grid. And this is helpful for accommodating complicated geometry. If there is lot of curves etc., then complicated geometry can be nicely handled in unstructured grid. An unstructured grid is helpful for finite element method specifically. Okay, and it helps also finite volume method, because these can be considered as one of the volumes, and on one of the volumes or one of the elements, depending on finite volume and finite element. So a little bit of note about this structured grid. So regular or structured grid consist of families of grid lines with the property that members of a single family. Okay, so if it is rectangular, it is rectangular and do not cross each other, and cross each member of the other families only once. This allows the lines given set to be numbered consecutively. So you can give numbering 1 2 3 4 like this. So this helps. This is a structured grid. So in 2D you can either use 2 indices, or in 3D you can use I, J, K 3 indices, and this is the simplest grid structure since it is logically equivalent to Cartesian grid. Each point has 4 nearest neighboring in 2 dimension and 6 in 3 dimension, and one of the indices of each neighbor of point P differs by 1 factor 1, okay, from the corresponding index of P. So we generally give nomenclature y equal to 1 2 3 4 in that way. So this is a very easy to understand, and structurally this is the root for finite difference, and finite volume can also be done, and finite element can also be done, but unstructured can also be applicable there. is a little bit different unstructured grid, as I was telling that, but for very complex geometries the most flexible type of grid is one which can fit an arbitrary solution domain boundary. In principle, such grids could be used with any discretization scheme, but they are best adapted to finite volume and finite element approaches. The elements of control volumes may have any shape, nor is there a restriction on the number of neighboring elements or nodes. So, in structure there was clear that in 3D there will be 6 neighboring points, in 2D there will be 4, and in 2D there will be 2 neighboring points, but here there is no restrictions. In practice, grids made of triangles or quadrilaterals in 2D and tetrahedral or hexahedra in 3D. So, when you are, if you have started working with ANSYS Fluent, you will see that grid elements are there, and elements are of different shapes. Either if you are handling 3D geometry, you may get the tetrahedral, hexahedral, these are the shape, and you need to check the quality of the mesh. So, those checking will be based on these different shapes. Such grids can be generated automatically by existing algorithm, and if desired the grid can be made orthogonal, the aspect ratio is easily controlled, and the grid may be easily or locally refined. The advantage of flexibility is offset by the disadvantage of the irregularity of the data structure. So, here the data structure will not be uniform or regular like structured grid. Now, node locations and neighbor connections need to be specified explicitly. The matrix of the algebraic equation system no longer has regular diagonal structure. So, in regular structured grid we are getting a regular tridiagonal matrix, but here it may not be the same. The bandwidth needs to be reduced by reordering the points. The solver for the algebraic equation system is usually slower than those for the regular grids. That is why you will see that finite element solvers runs little slowly compared to finite volume one. Okay, because finite volume may work in structured grid also nicely. So, this is little bit of introduction of structured grid and unstructured grid. This concept you should just keep in mind. Now, we will take up another type of problem, because so far you see that we have understood the so what type of problem that we have handled is like this: delta T, delta means if T, capital T temperature and small t time, then we have taken expression like this: delta 2 T by delta x square. Okay, so this is unsteady diffusion equation in one dimension. We have understood how to discretize this spatial term, how to discretize this temporal term. Now we need to see that how we can take we can do the convective term discretization. Okay, so convective term means, because Navier-Stokes will contain in the left hand side, you will see that v dot del v, like that. This type of term is there. Okay, so that means what? This is actually u into uh, del u del x plus v into del v del y plus, in if it is 3D, then w into del w del z, like this. So, these are called convective terms. I explained you in Navier-Stokes. So, let us take a very small equation, species transport equation. Okay, so species transport equation with convection and diffusion both. So, in the left hand side it is this equation is showing some convection term, in the right hand side diffusive term plus some source term. This is diffusion constant and u is the bulk flow velocity. Now, in 2D, if we consider such an this delta t will be equal to del del plus del del, it is written, because in Cartesian it will be del del x plus del del y. Okay, or if it is other coordinate, you can take it different. Now, if we follow the approach of finite volume, then these are the representation I have shown you, that what is face, what is center, that part we have explained, and how the points are recognized. This is a central of any volume. These, all of these boxes are basically one control volume. Central, at the center the indices is given P, and at the right hand side the next element is marked as E. This is west, east, west, north, south in S, that is how the neighboring points are defined. in this 2D, and the intermediate line, it is known as face. So in case of a 2D, this is a line. In case of a 1D, it can be a point. In case of 3D, it will be a face. Okay, so this is east face, west face, north face, south face. So this is how, and these are the dimension means width of each of the volume element. That this part we have shown in the last class. But now we need to integrate that equation, that convection diffusion equation, and it has second order differential equation, right? So second order differential equation means what? So second order differential equation means the second order is there. So if you like to get rid of it, you need to integrate 2 times. So 2 times integration is needed to get the solution. So if we do it, the integration of the first derivative will give you this one based on that on the terms that is given here in a control volume approach, and this is the integration of the second derivative. So you can get, and finally after doing the second integration, and if you write all those differential terms in this manner, in this algebraic form, and then if you rearrange little bit, you will see that the equations will be of the format like this. And this part we have seen in the last class, that how this algebraic equation can arise. Okay, so these are the algebraic equation which you can get after adopting the control volume algorithm. Now one important part here is that, let's say you have a control volume approach, and as you know, it is a, this is 1 point, this is 1 point, this is 1 point, this is 1 point. Now you need to your values, let's say velocity, pressure, whatever, you are storing it here, and it is here. Now since you are integrating in control volume approach, you should get the values in these intermediate points. Means from the central of the volume you should get the value at this face, because this, the value of any variable at this face is important to know. Let's say if you have, you know the u at this p point, this, if this is p point, then you must know what should be the value at this east face of this up. So how to do that? We need to do some interpolation. Okay, interpolation between this point and this point, and we need to find out. Now there are so many interpolation mechanism, interpolation schemes are available, that you should remember, because this you need to specify whenever you are giving programming or solution, doing some solution in any CFD solver. So let us see some of this algorithm, how these variables can be interpolated between this face and the center. So the first one is the first order upwind scheme. So first order upwind scheme is the most simple one. So if you have a point, so these are the two control volume. Okay, this is the central and this is the right hand side, and this is the flow direction. So your flow is moving in this direction. So what I need to know, because I need a variable, let's say phi p, phi x is the variable. So its value at p point is phi p, and I need the value of this phi and the value of this phi at the next point is phi e. So in this, between these 2 points I don't know, so I need to interpolate it. So here what is done, that whatever value the at the p point it is it, so you just interpolate it to the face. So directly straight interpolation. This is first order upwind scheme. So in the upward direction of the fluid velocity, you just transport it considering the same value. So consider whatever phi p value is at the center, the same value existing at the face. So this is called the first order upwind scheme. This is the simplest numeric scheme. It is the method that we discussed earlier. We assume that the value of phi at the face is same as the cell center value in the cell upstream of the face. The main advantage are that it is easy to implement and that it results in a very stable calculation. But it also it is very diffusive. Gradients in the flow field tend to be smeared out as we will show later. So this has some disadvantage. Okay, so this is because this is the very simplistic scheme. It has a lot of disadvantage, you cannot get sharp interface, etc. So but remember that concept is that the value of the center is assumed to be same at the phase in the direction of the flow field. Now comes the second order upwind scheme. So second order upwind scheme, what it
Sir,
states, yes,
so in
yes.
CFD, I mean, are we actually trying to find out the values at like the interfaces or actually the points like P and capital D?
uh, both are true, I would say, because in CFD my final objective will be to get the value at all the points. Okay, let's say if you have a computational domain like this, okay, and I have n number of grid points like this. Now depending on the method that you are adopting, you are calculating the values. If you use finite difference method, let's say, okay, then what we are doing, we are finding the values at these particular points. Okay, and what we are assuming that we will choose the grids in such a way these points will be very close to each other. Okay, in finite difference, remember finite difference this is, okay. So we will take a very small value, this width of this cell means this distance between these 2 points will be very close to each other.
Right.
So when you are plotting, that's why we are plotting the contour diagram. So contour diagram, that diagram will not give you any discrete values. You will see that a color representation or a graphical profile will be these, which will be continuous in nature. Although you are calculating it at discrete points, when we are plotting it, we are trying to see it, we are plotting it as a continuous function because we are taking very small grid size.
Right.
Okay, now this is finite difference. Now in finite volume, what is happening? The instead of points, we are now calculating at the center values. Okay, now there is a concept which is known as staggered grid, which we will discuss in the next class tomorrow. So what I just like to give you a sense like this. It will be clear in tomorrow a little bit more. So let's say in control volume, in finite volume approach. So what, instead of point, now we have boxes. So these volumes are there, right? So I have, let's say this P point is at the central point and here is phase. Now if you keep at the center, if you store all the values u, v, w, pressure, temperature, if you, these are the main variables, right, of the simulation. So velocity component, pressure, temperature. So if you store all the values at the center, then there is some problem. Okay, some numerical problem will arise. We will discuss that later on. So what we do here, we use a concept called staggered grid. So staggered grid means you store the pressure, temperature at the center and the velocity you store at the face. Okay, so we will store the velocity at the face and pressure, temperature, etc. at the central point. Okay, since both are at different positions, that is called staggered grid. It has some advantage. So that will be clear to you in the next day. But your answer is that the solution has to be calculated in finite volumes method in both the points. Okay, in
I
P.
mean, for very simple problems, can't we just neglect the solution at the interface? I mean, if the grids are like very small, like tends to zero.
That is for your understanding, for your demonstration, you can consider that those are continuous because we are in any way taking very small volume element. Okay,
Yeah.
but numerically when you are solving something, because in finite volume method what we are doing, you have a dy dx term in your equation, you are integrating it over a control volume.
Yeah.
Now integration can be done only on a continuous function, right?
Mm.
So this has to be continuous. So if you have a discrete point here, you cannot do that. At least you have to have a continuity between these points. Means your function should be continuous. The phase should be from the center to the phase, the value should be known, right?
Mm.
So that's why we are using these interpolation schemes, these first order, second order, these one. So second, as first order was showing that if you have a p value here, you just consider that same value here at the face. But here in second order, instead of taking this first value, you consider the earlier cell value and take join these two with a straight line and interpolate it. Okay, so this is little bit means development means than the first order appoint scheme. Okay, so this is for solving the mathematical equations you need to extrapolate, you need to know the values. Okay, you cannot, if you there the discrete values, then you cannot do the integration. Clear?
Yes, sir.
Okay. So this is second order. Then there is another scheme called central differencing scheme. Central differencing schemes means what? That instead of only interpolation, you take the value at the P point and take the value at the next neighboring cell point. You join them and whatever join them with a straight line, and whatever the intermediate value will be there, you consider that thing as your phase value of that property. Okay, so if you have velocity up here and ue here, not only velocity, you can take any property here. Let's say temperature Tp here, Te here. Then you just join it, and whatever the intermediate point will be there, so that you consider as the value at this phase. So this is called central differencing scheme. Then there is called quick scheme. This is very popular. So if you run fluent ANSYS fluent, you will see that by default options is this one, quick scheme. So quick stands for, because finite ANSYS fluent is a finite volume solver. So these schemes, interpolation scheme you need to mention. So quick stands for quadratic upwind interpolation for convective kinetics. Okay, so quadratic. So this is basically important whenever there is some convective term. We were not bothered about so far in whatever example we were studying, those are conductive problems. Steady state conductive first we have taken unsteady convective today. But the moment convective terms comes, okay, so this is this interpolation terms becomes important. Okay, schemes becomes important. So we need to identify that what is quadratic upwind interpolation convective kinetics. So this is a quadratic curve. So what it is considering, that this is your P point, this is E point, this is W point. You take all these 3 points, this point, this point value and this point, and then you feed a quadratic curve like this, and that quadratic curve will cross this face at a particular value of phi. So that will be considered as the phi e value of this scheme. So this is much more accurate. It was found that this is much more accurate. So quick scheme, you will see that it is given. So not only is quick, there is if you like to do research in this area, you will see that there are so many researchers who use different type of new novel schemes to improve their accuracy. Okay, because numerical process takes place in millions of grid, sometimes millions of grids are handled. Okay, so these schemes in those cells becomes very much important. Okay, this specifically for convective part. Okay, so this is all today. And now before wrapping up, I will just show you that how things are moving. Uh, our final objective of CFD is to be able to solve Navier-Stokes equation numerically, right? As I told you at the very beginning, that we will try to solve the Navier-Stokes equation. Now, Navier-Stokes equation has is a very big equation. So if you recall, it is having like a term like this, del u del t plus u dot del u plus equals to minus del p, or I can say the del p del x. If I write it del p del x, then mu into del 2u del x square plus rho g. So this is the standard form of Navier-Stokes equation. So you have a unsteady term, this is an unsteady term, this is a convective term, and this is due to this the whole system becomes nonlinear, right? And this is pressure term, this is your viscous term or diffusive term, and this is body force. Okay, so uh, we intentionally started with heat transfer problem. We have not yet touched the and because this is a nonlinear partial differential equation, we have not touched it yet, because and it is not also single-handedly solvable. That means if I consider this equation, you see that two unknowns are there, u and p. So this single equation you cannot solve, you need another equation. So that comes in the form of continuity equation, I have told you. Now why we have not started it at the beginning, because it will be very big, you cannot understand. So we moved step by step. So what we took, we took only this term. So we took only del 2t del x square equal to 0 in terms of heat transfer problem. So we took only this diffusive part. So diffusion in heat transfer is conduction basically. So we took the conductive equation, and then sometimes we took the source term, we have given it as S. So this S will be equal to 0 like that. So this equation we tried to solve using finite difference or finite volume method. Okay, because this is the most simple part. Then we tried to invoke today in this temporal part. So today's equation, today what we have done, we have taken an equation of this form. So I am writing instead of velocity t, because in heat transfer it will be t. So del t will be equal to what we have taken this part also, mu into, mu means this is alpha in heat transfer, del 2t del x square. Okay, so the reason is that we have tried to invoke this also. Okay, so first we have solved only this part, then we have incorporated this part. So this will teach you that finite difference what, finite volume what is finite volume, and how to use forward difference, backward difference, central difference, etc. Then today we have taken up this part which show you that how to use explicit method, how to use implicit method, how to use Crank-Nicolson method, what are their advantages and disadvantages, what are the associated stability criteria. Okay, and so these things we have. Now in the last part, in the last few slides, if you look, we are just trying to take an example of species transport instead of heat transfer, because the same equation can be formulated for heat transfer also. So we tried to take a convective equation like this. So where steady state we have not taken this steady state, this term was there and this term was there. So the equation was like this, u into del u equal to mu into del 2u del x square. So this part we have tried to use via finite volume method, that you can see, and in doing so you see that interpolation scheme is important. So this part, this equation if you see, okay, so this is the convective equation and this is the diffusive equation, source term is here. So this we tried to solve on the finite volume method, and this is the equation that we will get finally. And here interpolation schemes becomes important. That's why we are discussing little bit of upwind scheme, second upwind, central difference, and then quick scheme, etc. Now, so step by step we are trying to move, but still our final objective is to solve the Navier-Stokes equation in its entirety. Okay, that means what our objective will be next, like this Navier-Stokes del u del t. I am writing once more, u dot del u 2 minus del p del x. I am writing it one dimension, mu into del 2 u del x square plus rho g. So now we need to solve it in its entirety. But so far we were one by one, step by step, we are trying to explain that how the equation can be gradually moved. So basic building blocks are with you right now. You know this. Now in the next class we will take up the step to see how these equations can be solved, because this has another, because we know how to handle now the diffusive equation, how to take this part, how to take this unsteady part, that is known to us. But the remaining thing that is exceptional here is the pressure part. This pressure part, that pressure and velocities are coupling, pressure velocity are coupled things, these are related, and that's why individually you cannot do it, you need to take the help of this delta del dot u equals to 0, that is the continuity equation. So these two equations, this pressure and velocity coupling will be done with the help of this continuity equation. Okay, so that makes the thing little bit difficult, that's why people struggle little bit for understanding. So we'll try to understand this particular part in as much simpler manner as possible, and that will mark the end of this course. Okay, so that will be covered tomorrow. Okay, so I will stop here now. it is open for questions. You have whatever doubt you have, any questions in your mind, please ask now. Any questions? Okay, no question, then it is fine. I will again.
Sir, for the
Yes.
transient 20 problem, can you show the slide once, please? The transient 20 problem that we
Okay,
started with.
okay. Just 1 minute. This is the problem that we have started today. Yes, tell me.
Is the next slide, please? The next one.
This one?
Yes, sir, this one. Yes, sir.
Yes.
Sir, here we are considering the theta m minus 1 equals to theta m plus 1. So because at the temperature at the point 3 and at the point 5, those three are same, right?
Right,
Sir,
right.
this is because only the geometry of this problem is
No,
symmetrical.
not geometry.
The
Whenever
temperature
you,
difference is
I
same.
understand your problem because you like to because at the boundary condition be of two type, right? One is that as in the left hand side, your Dirichlet boundary condition is
Yes,
given in very
yes,
precisely
yes. That is specified the temperature.
specified, but here instead of that we are uh, just okay. So here the values is given explicitly defined. Let's say t equal to 100 is given in the left hand side, and the right hand side your Neumann boundary condition given, that
Yes,
is in the form of dx
delta
dx
L S.
it equals to 0. So this is not at all geometry specific. Generally at anywhere you this any geometry it can come. Okay. Now
Yes.
whatever be the geometry, if you have a boundary condition like this, that the gradient is 0 at that point, this
Okay,
is
okay.
means what? The gradient is 0.
Yes,
So
sir.
gradient 0 means if any
That
variable has a gradient 0 means what?
that is
Now,
one maximum or minimum value that is
right.
that.
So in order to understand that, you need to assume that there is a virtual point,
Yes,
and either this is having a maxima or a
or
minima or
minimum.
a maxima.
Yes, sir.
Right now, dtdx is zero possible at this point. Either it is maxima or minima. So that
Yes.
is only possible when this virtual point will be having the same mirror image of this point.
Uh,
Right. So this you can assume. This is an assumption to manage the Neumann boundary condition. Okay. So instead of this T5 and this T3 will be equal, because T5 is an unknown point, right? It is a virtual point. You cannot take it into the solution. So you can express T5 in terms of T3 with these
yes.
assumptions. Okay,
Yes.
so that is what it is done there. So that is why it is the 2m minus 1. So instead of so if you ideally write it, it should be T3 minus 2T2 2T2 plus T5 by delta x square, right?
Yes.
Now since
Yes.
these
Yes.
two are equal to, we are doing it 2 theta m minus
Two,
1.
three. Yes, sir. Minus two.
Yeah.
Okay.
So
Yes.
instead of dt by dx is equal to 0,
Uh,
a number is given like dt by dx is equal to say 5. So
hmm.
can we apply this mirroring technique then also?
Then also then also yes, that case you need to calculate it. Okay, here we are assuming that gradient is 0, that's why dt dx equal to 0, that's why you can directly replacing t3 equal to t5. If some value is given, in that case t3 sorry we are doing here t5 equal to t3. So if
Hmm.
some value is given here, let's say 5 is given. Okay, so in you discretize it, you will find that t5 will be equal to t3 plus something, some value, something like 5 point something, some value will come here. So instead of T5 equal to directly T3, you put that T3 equal plus 5. Let's say it will not be
No, no, I
5,
mean,
but I am just
I'm not
giving an
saying like
example.
the condition is given that t is equal to 5. I'm
Hmm.
saying dt by dx is equal to 5.
What please repeat.
Yeah. here the condition you have given is dt by dx is equal to 0, right? If instead of this condition, a condition was given like dt by dx is equal to say 5. So then could we have applied this mirroring technique?
No. No, mirroring technique you cannot take in that case. The mirror point, image point will not be there. But in that case also you can find out the value of T5 based on that derivative value. So what dt dx is suggesting that this 0 indicates it's a maxima or minima. Now you are saying that instead of 0 it is having some value.
Exactly.
Right, but that is giving you an indication that what should be the value of this 5 at this point. If you interpolate, your gradient is given. So what we are doing everywhere, you can get any value ti plus 1 which will be equal to ti plus, if you know the gradient, dt dx into dx. This can be done with Taylor series.
Okay.
It is clear or not? Now here I am taking these as 0, that's why these two are equal, as it becoming mirror point, image point. Now if some value is given, then you explicitly mention that value, ti plus 1 will be equal to 5 plus some value will be there. So in that case these t3 and t5 will not will be equal, it will be different. Okay, but still you can express t5 in terms of t3. Is it clear or not?
Yes.
Okay, so you just simply remember the Taylor series. If your gradient is known to you, so let's say this is 5. Now I can write ti plus 1 will be equal to ti plus 5 into dx. Now dx is known to you, right? Dx is the grid size. So let's say its value is 0.1. So what will be the value? So ti plus, it's better to write here, ti plus 1 will be equal to ti plus 5 into 0.1. If my dx is 0.1, so your value will be ti will be equal to 0.5. So if I take I equal to 2, so your or I equal to 4, then t5 will be equal to t4 plus 0.5. So that is how you can express this virtual point in terms of the known ones. Clear?
Yes.
Okay, so in addition, it will be, means in case of any value is given, you need to do an extra step. Okay, it may not be directly calculated like this 0. So but you can you can definitely calculate that part. Any more question? Good question. I will ask you to, if you are interested, this is very simply explained in the books of Professor P.S. Ghosdostidar in computer fluid dynamics and heat transfer. I will give you the reference of the book in the next class. Okay, so you can, this is a small book but beautifully written, so you can understand all these things very easily. So any more question?
No, sir. Thank you.
Okay.
So, what is the name of the author you said? The book?
P.S. Ghosdostidar, Parthasarathi Ghosdostidar is professor of IIT Kanpur. So it's a small book. I'll give the details of the book in the next class. I am using the snapshot of that book only.
Okay, sir.
So is it being means, are you understanding little bit? Means what is you means, is it okay? Or the
Yes, sir.
way it is moving on? Okay. Okay, that's good. Let us see at the end if you can understand the Navier-Stokes equation little bit. Then with this that knowledge, if you start working, then during your journey of learning you can understand so many things. Okay, I am giving just the overview of CFD. Okay, so if there is no more questions, let us call it a day. We will stop today. We will again meet tomorrow 10 a.m. For the final session. Thank you. Thanks for your attention.
Thank you.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you.
Thank
Thank
you,
you so
sir.
much. Thank you.